Hello, this is David. Welcome to Linda Allen, Chapter 3, Putting Value at Risk to Work. And just like the previous Chapter 2, this is a well-seasoned reading in the FRM syllabus, having been in the syllabus for over a decade. And it primarily concerns value at risk. So this is one of the key chapters in Part 1 that is about value at risk, its strengths and weaknesses, and the various approaches, with an emphasis on what Linda Allen calls the delta normal approach. And that is a specific class of the parametric or analytical approach to value at risk. So we will take a look at this. And the first learning objective is explain and give examples of linear and nonlinear derivatives. And so this is a key frame in the chapter, this idea of linear derivative versus nonlinear derivative. And so a linear derivative is one in which the relationship between the derivative and the underlying pricing factor is linear. It does not need to be one for one, but the transmission parameter or delta needs to be constant for all levels of the underlying factor. And so I would just highlight that aspect of the definition here in Linda Allen, right? The definition of a linear derivative is one in which the delta is constant, and a nonlinear derivative has a delta that is not constant. You may recall in the stock, so this is really a stock option class terminology, and if the delta is constant, then the gamma is zero. So this is another way we could say this, is that the linear derivative is one where the gamma is approximately zero, and a nonlinear derivative would have a gamma that is non-zero. So related to this idea is that all assets are effectively locally linear, and I've highlighted that. And we're looking at the stock option context, but it applies all the same to the bond asset class context, right? When we study value at risk and risk measurement, at the end of the day, the two asset classes that we focus on in the FRM as foundational or as platforms for learning, I think it's safe to say, are equity and stock options. And then in the case of bonds, it's the duration convexity frame, and they are closely related. They are actually manifestations of the same Taylor series that comes up in a later slide. But the key idea here is that all assets are effectively locally linear, and this applies to option delta in the same way that it applies to bond duration, right? So on the left, I have call price versus stock price, right? This is the familiar nonlinear relationship between the value of an option and the underlying stock price. And over on the right, I have the delta of that same one-year call option. And we can see here the delta is not constant. So this is meeting this definition. The stock option here, this is an illustration of that definition of a nonlinear derivative because the delta itself is not constant. This delta here maps to this by being the slope, right, of the line that's a bad line point of tangency. But if I take a point of tangency, right, at each given point there's a line that doesn't cut through this chart, but actually just hits it on the point of tangency, and the slope of that line is the delta, right? So we start down here, that tangent line has a slope of pretty much close to zero, and then it gets steepest here in the middle at the money. No, or actually that's not right, sorry. It gets increasingly steeper, right, as the underlying stock price increases. So we see the delta increasing, and the delta itself is not increasing in a linear fashion.